In this video, I want to take a look at some integrals, improper integrals involving exponentials here. This is just your decaying exponential. It looks like this. I'm going to start from any value of a. It could be positive, could be negative, could be zero, it doesn't matter. And then I'm integrating to infinity. So I'm trying to figure out that area, right? That area under that curve. We've seen on other ones where this comes out to be positive, comes out to be finite, and somewhere it comes out to be infinite, so we'll see what it does here. Anyway, the integral of e to the minus x is minus e to the minus x, and you're evaluating that between a and infinity. So you got minus e to the minus infinity minus e to the minus a. A lot of minuses there. This is right here is what's the kicker on this one. Is this finite or is this infinite? Well, the thing is, e to the negative infinity, e to the negative anything means e to the, 1 over e to the anything. So that negative exponent means you're putting that in the denominator. So when I'm looking at an e to the minus infinity, it's like a 1 over e to the infinity. Well, e to the infinity goes to, e, that grows hugely. E to the infinity, e to the x grows this way. So as I plug in bigger and bigger values of x, that gets very big. So anyway, this is 1 over infinity, which is 0. So this bit right here, well, it's negative 0, but that's still 0. So I got 0 plus e to the negative a. So this turns out to be just 1 over e to the a. So for any value of a here, well, there's no vertical asymptotes to get in the way, so any value of a, integrate as you head to infinity, and that's a finite value, 1 over e to the a. Okay, so the next one I want to do is very closely related. About the integral from a to infinity of x, e to the minus x. Okay. This looks a little bit different in that it passes through 0 here. It looks something like that. Still, as you integrate from a to infinity, it looks like there's a possibility of finite area. If this function was not headed to 0, then I would say there's no way that could be finite. But as long as it is headed downhill towards 0, you got the possibility of having a finite value here. So I do this just because I want to see integration by parts in this, and there's another thing that happens as well. So to do this integral, we got to do parts. So u du, v dv. We're going to put an x here, and e to the minus x dx there. So that integrates to minus e to the minus x, and this is just dx. Now this is a place where my own notation sort of falls down. It's not quite good enough, so I got to be careful with this. As I do this, u times v, so x e minus e to the minus x, evaluated between a and infinity, minus the integral of from a to infinity of e to the minus x dx. There's an extra minus sign, so that becomes a plus. Okay. The thing that happens here is as I try to evaluate this thing, I've got this minus infinity e to the minus infinity minus a e to the minus a plus whatever this integral is. Actually, we just figured this integral out, didn't we? We just figured that integral out above. It was 1 over e to the a. But this bit right here is the thing that's bothering me, because this is an indeterminate form. This is an infinity times 0. This bit right here is 0. And infinity times 0 might be anything. Now, as you do more of these and you get more comfortable with this, I'm willing to say that this is a polynomial infinity. This infinity is coming from that x. And this is an exponential 0. It's headed to 0 like that exponential does. And exponentials beat polynomials any day. But the thing is, if I'm not sure of that, then what I need to do is I need to actually remember what I'm doing, and that this is the limit as b goes to infinity of negative b e to the negative b. Okay. And then what I do is I do set it up for L'Hopital's rule. This is the limit as b goes to infinity of negative b over e to the positive b. So now this looks like infinity divided by infinity, and I can apply L'Hopital's rule. So this is the limit as b goes to infinity. Take the derivative of the top, minus 1. Take the derivative of the bottom is e to the b. This is why exponentials beat polynomials any day, is that in L'Hopital's rule, polynomials eventually go away as you take derivatives, but the exponential is always there. This now looks like a minus 1 over infinity, but minus 1 over infinity is 0. So this thing right here is equal to 0, and I'm left with, so this stuff gives me an a over e to the a plus 1 over e to the a for a grand total of a plus 1 over e to the a. These two examples that I just did, both are functions which head towards 0 as x increases, but this second one, it doesn't go quite as fast. This x is trying to force it to go up, but the exponential is keeping it down. Okay. Be careful when you do this, that you're not just randomly saying, oh, look at that, infinity times something, that's going to be infinity. Right? The thing is, it's infinity times 0, so that's an indeterminate form. You're actually taking a limit here. So be careful as you do that. Take that limit. In this case, it turns out to be 0, and we're good to go here to get a finite value. And that's the value of this integral.